Hi, I'm Chris, and I would like to show you our new application in CADS package. It's the application which helps structural engineers to design and check raft foundations for domestic buildings. The application is based on the simplified approach, which is presented in the book Structural Foundation Designer's Manual, written by Curtin, Shaw, Parkinson, and Golding. You probably know another great book written by these authors, which is Structural Masonry Designer's Manual. Our application is based on Eurocodes, mainly on Eurocode 2 for concrete elements design. And I would like to highlight one thing, that it's not the application which you could use for every type of raft. It's because we use that simplified approach, which is valid for semi-flexible raft slabs. And this is actually the case for relatively thin ground-bearing slabs, which are used in domestic buildings or garages. If you would like to design or checked raft in multi-story concrete frame buildings, it's not the correct software. It's because in such structures, rafts are much thicker, much stiffer, and usually they are modeled as one element, which is transferring loading from many columns, many walls to the soil, where in our software, we rather check local parts of raft under local loadings, and we treat them as sort of separate virtual foundation paths or strip foundations, and we look at those local parts independently. Let's explain a little bit principles of the approach used in our software and presented in the book. We've got two scenarios we need to consider. First, we are checking bearing of our raft on the soil, and we also need to do all related checks. And second scenario is we are assuming that local depression may occur under the raft. So our raft will act over the depression as suspended concrete element, and we need to find internal forces in such element, slab or beam, and we need to check reinforcement and do all necessary related checks. When we have a domestic building, we have a layout of walls on ground floor. Those walls may be cavity walls, single leaf walls. They may be bearing, non-load bearing. We may have also some point loads, and those walls are standing on raft slab, but very often under heavy line loads, we are providing in domestic buildings rafts local thickening. On the right side of the slide, I have shown them with blue lines. And the idea of those thickening is that they will act in similar way as strip foundations. And as I mentioned before, in case of semi-flexible rafts, we are not checking raft as one whole element. Instead, we are checking local smaller parts of rafts. So on the right side, I showed them with circles. continuous and continuous line and hidden line circles. So as you can see, there are many possible cases we should check, but this is only in theory because we know that generally our slab and our slab thickenings have the same properties, similar geometry, similar reinforcement. So we actually need to find only couple critical locations, and we need to check them. So in this case, I would probably check only those 4 cases which are shown with solid thick red lines, and how to justify which parts need to be checked. Generally, we are looking at loadings. So if we have corners, we are checking this corner, which has heaviest loadings. Sometimes it's not easy to justify because we may have different arrangement. For example, for one corner, we may have single leaf walls with heavy loads. For other corners, we may have cavity walls with smaller loads, but there are also different eccentricities. So I would say in such case, we probably would have to check more cases.
We have 4 types of situations which we can check in our software. These are 3D diagrams showing geometry. I am not showing loadings here, it's just to show the idea. So we have internal slab. This is just ground bearing slab, loaded mostly with uniformly distributed load, but you may try to check it as well for some line loads and point loads which are not heavy, like partitions, non-load bearing partitions, and it may work. Then we have slab with internal thickening. This is in case when on our slab there are much heavier loaded walls or some columns, so we need to provide sort of spread foundation. Edge case is the same, but where we have walls standing on the edge of our slab. If those walls are not very heavily loaded, it is possible in our software as well checking the slab without thickening. And corner case, similar to edge case, but those 2 edge thickenings are meeting in the corner, and we can check it for point loads and line loads. There are a couple variations of the thickenings possible to define in our software. So we have internal slab thickenings where thickening is just rectangular beam or beam with chamfered edges. For edge and corner cases, we may check it for just plain slab or rectangular beam or rectangular beam with one edge chamfered, and also we can check that beam if we have nib. Now let's take a look at our application.
We have generally 2 parts in the window, the same as in other our applications. On the left side, we have canvas where we can present graphical results or reports, and on the right side, we have a panel with tabs where we define input data. And in this case, in case of Raft applications, we have 1, 2, 3, 4, 5 tabs. And first, we would start filling tab defaults. This is tab with all properties of slab and beams, internal beams and edge beams. So we define reinforcement, geometry, and the reason is that later when we define cases for our Raft locations, we can load those properties defined in defaults, so we don't need to fill all data again and again. So we have other tabs are geometry, where we can define our cases. So we have internal slab cases, internal beam cases, edge cases, and corner cases. There will be a list of our elements. Second tab, I will go and show examples in a minute. Second tab, materials. There is nothing much to explain. We define concrete and reinforcement grades. We defined partial factors and hardcore fill below raft and soil. And there is one thing I would like to talk about, which is custom depression diameter. So there is no guidance in Eurocodes how to estimate depression of assumed how to assume diameter of assumed depression. However, in the book I mentioned at the beginning, there is a table which provides some guidance, and in our application we can use that guidance as well as user can provide his own depression parameter, diameter. Third tab is loadings, so I will also show it later when I define geometry, but what I would like to explain are some properties in tab settings. We have national annex, which is doesn't need to be explained, and we have also 4 other parameters, and those I would like to explain. So first we have fixed beam bending moment factor and things from UDL, and fixed beam bending moment factor for point load. As I mentioned earlier, when we have depression, our elements are spanning over that depression. So in case of thickenings, we have beams which are suspended over the depression, and we need to calculate internal forces in such beam. So those factors are factors in the formula M alpha times P times L in case of point load, or M is equal alpha times Q times squared L in case of UDL. And factors alpha are used to calculate hogging and sagging moment. As we know, for example, for fixed beam ends with UDL from theory of elasticity, the hogging moment and sagging moment are different. Hogging moment is WL by 12, sagging moment is WL by 24. However, using moment redistribution and simplifying things, we are assuming that hogging moment and sagging moment are the same, and we are allowing user to define that factor. Other two parameters properties in settings are cantilever length limits for slab and for beam. What are they? Generally, when we have point load, which is standing on point load or longitudinal line load, which is standing on slab or on beam, we, in case if that element is very stiff, we can assume that it can spread load through over the long distance L1. However, when our slab or beam is not very stiff and is semi-flexible, the stresses below the bearing stresses below the element are non-linear, as it's shown on the second diagram, and we cannot assume that we have UDL stress below slab. So we are limiting that distance where we spread the load by providing a limit where that cantilever LC is n times element depth, and we allow user to provide those factors. I think 4 or 5 are reasonable values in such case. Let's go back now to the CADS application and let's try to define internal slab case. So first let's go to geometry. We can define our slab by clicking editing. Most of those properties are self-descriptive and I am not going to discuss them. However, I would like to explain something a little bit more about reinforcement location, top and bottom or top. On the left side, where we have slab with top reinforcement only, we can spread our loading only assuming that load is spreading under 45 degrees through the concrete slab and through the fill below the concrete. So our spread distance is quite limited for soil. However, when we add top and bottom reinforcement, we can spread our loadings over much longer distance because now when we have pressure from bottom, that pressure is causing tension in bottom of the slab, but because we have reinforcement, we need to try if this reinforcement can resist a bending moment from that pressure. And in similar way, we are dealing with edge beams or thickenings and corners. As you can see on left side, for top reinforcement only in slab, the spread distance is quite short. However, with bottom reinforcement, if we check our slab for bending moments, we can spread that load over much longer distance. And going back to the slab, let's assume that all properties are now defined, and materials and settings, we can now define loadings. So when I add load case, let's say first load case, and it will be type slab UDL, permanent, it will be 1.2 Newton per square meter, let's say it's lot of finishes, and variable 1.5. Let's add another load, and let's say it's load 1. So that we have some couple of different types. Let's say that will be longitudinal load, and it will represent low load bearing masonry wall standing on the slab. So let's say there is only permanent load 15 kilonewton per square meter on width 100. Okay, it's 100 or 140. And now we can check if that case is okay. So we can go first to summary report, so we can see our table with some checks, and we can see what is failing, what is passing. So first, slab cantilever bending for bearing pressure bottom reinforcement is failing. Let's go and check. Okay, so let's change that reinforcement. Okay, so now it's passing. Okay, all checks passing. We can look at detailed calculations as well. And in detailed calculations, we can see all formulas, all steps. So it's quite nice to find what the algorithm does, and what all we can check all steps, intermediate steps of our calculations. Here I would like to explain how we calculate depression and checks related to depression in our software. In the book approach on the circular slab suspended over the depression, we may have walls and columns standing on it, and simplified approach is that we are replacing such loads with equivalent uniformly distributed load on circular slab. But in our software, we are checking square depression instead of circular depression. This simplifies calculations and gives more or less the same results as for circular slab. And so instead of circular depression with diameter D, we are checking square slab with dimension 0.5 D. In case of slab, internal slab, we may have two possible scenarios. One, when we have top and bottom reinforcement in slab, and second, when we have top reinforcement only. On the left side, I've shown option where we have top and bottom reinforcement. So we may assume that our square slab is two-way bending, and it's fixed at edges. So we need to find internal forces, bending moments and shear forces in such slab. But in case of square slab, it's quite simple because we can use formulas presented in engineering tables. If we have slab with top reinforcement only, we cannot assume that slab will resist sagging moments. So we have virtually broken slab in the middle, and we are checking to separate independent cantilevers. This allows us to check our slab for top reinforcement only. Now we can check other case. We can add other case. For example, I will add edge case. Thickening type, we can have beam with chamfer, beam with nip. Let's say we have beam with chamfer, slab thickness, let's say 50, beam depth, let's say 450, beam width 50, hardcore depth 100, chamfer angle 45, and cover to reinforcement for beam, let's say bottom. Top bar diameter 20, okay, number of top bars, or let's say 3, number of bottom bars 3, link diameter 10, let's say space 50, number of legs 2, reinforcement location top and bottom for slab. And there is also option adjust adjacent slab, but I will explain it in a minute. So let's okay, and let's define now loading for our beam. Okay, sorry, it's not internet. So again, let's define type UVL. So it will be 2.5. And let's add another one, which will be longitudinal load. So let's say that will be external leaf of our cavity. So let's put it as 12 kilograms permanent. 12 variable 0, width of the wall is 100, offset from beam edge, let's say 50, and here edge. So that green line is that wall, and let's add another wall. Let's say in this case we put ball, so let's play 25, 15, 25, 15, 100, and let's say that will be 100. So we have now second line load. Let's calculations. Okay, there are some lines. Adjacent slab bending with load eccentricity over top reinforcement. Okay, so again, it's not enough reinforcement in slab, so I will change that. I will explain in a minute what is that adjacent slab bending with load eccentricity moment. Okay, and now we have all checks passed. Let's now talk a little bit about check related to load eccentricity moment. When we are checking bearing stresses
under our Raft parts, we are assuming that they are uniformly distributed, but this is true only in case where our resultant loading on the raft is acting exactly in the center line of assumed raft width. In most cases that's not true, and that eccentricity of such load is causing additional bending moment, and eccentricity equal P times E. That was shown on the left side for internal slab thickening case. For edge case, it's a very similar idea. We've got additional bending moment from resultant load eccentricity. And such additional moment need to be transferred safely somewhere. And we have two options. One option is we could transfer this moment through our raft part to the soil, and this would cause non-uniformly distributed stresses. It would be sort of triangular stresses under the raft. And second option is we could transfer this additional bending moment to adjacent raft parts. And in our software, we are using second option, and we transfer our load to our additional bending moment to adjacent slabs or adjacent beams in corner case. This is also case described in approach in the book I mentioned at the beginning. Let's take a look how it is transferred to slab. In case of internal thickening, we have two options. On the left side, I've shown a situation where adjacent slab have top and bottom reinforcement, and in such case, our eccentricity moment can be spread between left and right adjacent slabs. So each of them will resist 50% of such moment. However, when we have top reinforcement only, this is the case on the right side, only one slab can transfer moment. This one where we have top reinforcement and tension from bending moment will occur at top of slab. So on the left side, if we try to transfer bending moment to that slab, tension would occur at the bottom of the slab, and because we don't have reinforcement, bottom reinforcement, we would not be able to resist that tension. So that's why we transfer whole moment to one slab. In case of edge thickening, is similar. We can transfer our eccentricity moment to adjacent slab. And if we go back to application, we can see that when we define geometry, let's edit our slab. At the bottom, we have option adjacent slab, so that's where we can choose our slab. And if we calculated in our software such adjacent slab before, and it's on the list, we can choose it. However, if we haven't, we can choose option none, and in such case our software will create additional case with such internal slab, and will add loadings into it based on our edge case. and we'll check that slab for this additional bending moment. And the same we can do with internal beam. I will just quickly add some internal beam, and we can see there is also such option when we can choose none or slab if it was calculated. Slightly different, we check corner case. In case of corner, we are assuming that our corner area is loaded in its gravity center with resultant point loads and resultant bending moments in direction X and direction Y. But in this case, to our corner, we have adjacent beams B1, beam 1 and beam 2, and those beams are much stiffer than adjacent slabs, so we assume that those beams will resist additional eccentricity moments. So we just ignore slab, saying that our beams are enough to resist that moment. And when we look at section AA, I'm just showing eccentricity moment, blue eccentricity moment in that direction will be transferred to beam 1. And in the software, if we go back to software, if I create a corner case, again we have at bottom option when we can choose beam which adjacent beam which will be checked for this additional moment. But if we choose option none, again in the background software will create will create those edge beams and will load them with loadings defined for corner case, and will check those beams for additional bending moment.
So I think that's all I wanted to show you today. I hope you will find our software useful, and I hope you will enjoy using it. Thank you for your attention.